4.3 Stages of Sleep. Learning Objectives. By the end of this section, you'll be able to differentiate between REM and non-REM sleep, describe the differences between the 4 stages of non-REM sleep, understand the role that REM and non-REM sleep play in learning and memory. Sleep is not a uniform state of being. Instead, sleep is composed of several different stages that can be differentiated from one another by the patterns of brainwave activity that occur during each stage. These changes in brainwave activity can be visualized using EEG and are distinguished from one another by both the frequency and amplitude of brainwaves. Sleep can be divided into 2 different general phases, REM sleep and non-REM sleep, or NREM sleep. Rapid eye movement, REM or REM sleep, is characterized by darting movements of the eyes under closed eyelids. Brainwaves during REM sleep appear very similar to brainwaves during wakefulness. In contrast, non-REM sleep is subdivided into 4 stages distinguished from each other and from wakefulness by characteristic patterns of brainwaves. The first 4 stages of sleep are non-REM sleep, while the 5th and final stage of sleep is REM sleep. In this section, we'll discuss each of these stages of sleep and their associated patterns of brainwave activity. Non-REM stages of sleep. The first stage of non-REM sleep is known as Stage 1 sleep. Stage 1 sleep is a transitional phase that occurs between wakefulness and sleep, the period during which we drift off to sleep. During this time, there's a slowdown in both the rates of respiration and heartbeat. In addition, Stage 1 sleep involves a marked decrease in both overall muscle tension and core body temperature. In terms of brainwave activity, Stage 1 sleep is associated with both alpha and theta waves. The early portion of Stage 1 sleep produces alpha waves, which are relatively low frequency, high amplitude patterns of electrical activity, or waves that can be synchronized. This pattern of brainwave activity resembles that of someone who's very relaxed yet awake. As an individual continues through Stage 1 sleep, there's an increase in theta wave activity. Theta waves are even lower frequency, higher amplitude brainwaves than alpha waves. It's relatively easy to wake someone from Stage 1 sleep. In fact, people often report that they haven't even been asleep if they're awoken during Stage 1 sleep. As we move into Stage 2 sleep, the body goes into a state of deep relaxation. Theta waves still dominate the activity of the brain, but they're interrupted by brief bursts of activity known as sleep spindles, as shown in Figure 4.10. A sleep spindle is a rapid burst of higher frequency brainwaves that may be important for learning and memory. In addition, the appearance of K complexes is often associated with Stage 2 sleep. A K complex is a very high amplitude pattern of brain activity that may in some cases occur in response to environmental stimuli. Thus, K complexes might serve as a bridge to higher levels of arousal in response to what's going on in our environments. Stage 3 and Stage 4 of sleep are often referred to as deep sleep or slow wave sleep because these stages are characterized by low frequency, high amplitude delta waves, as shown in Figure 4.11. During this time, an individual's heart rate and respiration slow dramatically. It's much more difficult to awaken someone from sleep during Stage 3 and Stage 4 than during earlier stages. Interestingly, individuals who have increased levels of alpha brainwave activity, more often associated with wakefulness and transition into Stage 1 sleep, during their Stage 3 and Stage 4, often report that they don't feel refreshed upon waking, regardless of how long they've slept. REM sleep. As mentioned earlier, REM sleep is marked by rapid movements of the eyes. The brain waves associated with this stage of sleep are very similar to those observed when a person is awake, as shown in Figure 4.12. And this is the period of sleep in which dreaming occurs. It's also associated with paralysis of muscle systems in the body, with the exception of those that make circulation and respiration possible. Therefore, No movement of voluntary muscles occurs during REM sleep in a normal individual. REM sleep is often referred to as paradoxical sleep because of this combination of high brain activity and lack of muscle tone. Like non REM sleep, REM has been implicated in various aspects of learning and memory, although there is disagreement within the scientific community about how important both non REM and REM sleep are for normal learning and memory. If people are deprived of REM sleep and then allowed to sleep without disturbance, they'll spend more time in REM sleep in what would appear to be an effort to recoup the lost time in REM. This is known as the REM rebound, and it suggests that REM sleep is also homeostatically regulated. Aside from the role that REM sleep may play in processes related to learning and memory, REM sleep may also be involved in emotional processing and regulation. In such instances, REM rebound may actually represent an adaptive response to stress in non depressed individuals by suppressing the emotional salience of aversive events that occurred in wakefulness. While sleep deprivation in general is associated with a number of negative consequences, the consequences of REM deprivation appear to be less profound. In fact, some have suggested that REM deprivation can actually be beneficial in some circumstances. For instance, REM sleep deprivation has been demonstrated to improve symptoms of people suffering from major depression, and many effective antidepressant medications suppress REM sleep. It should be pointed out that some reviews of the literature challenge this finding, suggesting that sleep deprivation that is not limited to REM sleep is just as effective or more effective at alleviating depressive symptoms among some patients suffering from depression. In either case, why sleep depression improves the mood of some patients is not entirely understood. Recently, however, some have suggested that sleep deprivation might change emotional processing, so that various stimuli are more likely to be perceived as positive in nature. The hypnogram shown in Figure 4.13 shows a person's passage through the stages of sleep. Dreams. The meaning of dreams varies across different cultures and periods of time. By the late 19th century, German psychiatrist Sigmund Freud had become convinced that dreams represented an opportunity to gain access to the unconscious. By analyzing dreams, Freud thought people could increase self awareness and gain valuable insight to help them deal with the problems they faced in their lives. Freud made distinctions between the manifest content and the latent content of dreams. Manifest content is the actual content or storyline of a dream. Latent content, on the other hand, refers to the hidden meaning of a dream. For instance, if a woman dreams about being chased by a snake, Freud might have argued that this represents the woman's fear of sexual intimacy, with the snake serving as a symbol of a man's penis. Freud was not the only theorist to focus on the content of dreams. The 20th century Swiss psychiatrist Carl Jung believed that dreams allowed us to tap into the collective unconscious. The collective unconscious, as described by Jung, is a theoretical repository of information he believed to be shared by everyone. According to Jung, certain symbols in dreams reflected universal archetypes with meanings that are similar for all people, regardless of culture or location. The sleep and dreaming research, Rosalind Cartwright, however, believes that dreams simply reflect life events that are important to the dreamer. Unlike Freud and Jung, Cartwright's ideas about dreaming have found empirical support. For example, she and her colleagues published a study in which women going through divorce were asked several times over a 5-month period to report the degree to which their former spouses were on their minds. These same women were awakened during REM sleep in order to provide a detailed account of their dream content. There was a significant positive correlation between the degree to which women thought about their former spouses during waking hours and the number of times their former spouses appeared as characters in their dreams. Recent research has uncovered new techniques by which researchers may effectively detect and classify the visual images that occur during dreaming by using fMRI for neural measurement of brain activity patterns, opening the way to additional research in this area. Recently, neuroscientists have also become interested in understanding why we dream. For example, Hobson suggests that dreaming may represent a state of proto-consciousness. In other words, dreaming involves constructing a virtual reality in our heads that we might use to help us during wakefulness. Among a variety of neurobiological evidence, John Hobson cites research on lucid dreams as an opportunity to better understand dreaming in general. Lucid dreams are dreams in which certain aspects of wakefulness are maintained during a dream state. In a lucid dream, a person becomes aware of the fact that they're dreaming, and as such, they can control the dream's content.